Okay guys, so welcome again to my channel. We're on day number 4 of the PiHut Maker Advent Calendar. So let's go ahead and open day number 4. So I'm just going to pull number 4 out the box. Another little bag here. And let's see what we've got in today's bag. So in today's bag, we've got a 10K potentiometer. We have the knob that goes on it, a washer, a nut, and 3 male-to-male jumper cables. So today we're exploring the wonderful world of analog. Until now we've been using digital signals with the buttons and LEDs in our calendar. Digital signals are strictly a 1 or a 0, high or low, on or off. It's one or the other and nothing in between. Analog signals offer a wide range of numbers to represent values instead, which is much more suitable for sensors, dials and similar components. Think of digital as a light switch. It's either on or it's off. Think of analog as a volume dial on stereo. You can twist the dial to gradually turn the volume up and down by small amounts. Our potentiometer can pass these analog signals to our Raspberry Pi Pico, giving us a gradual input with a wide range of values for us to play with in our code. What is a potentiometer? A potentiometer is a variable resistor. Our calendar already included traditional resistors for the LEDs, but these were at a fixed value offering a specific amount of resistance. A potentiometer is a resistor that can have its value changed by turning the knob. The potentiometer is in your box is a 10K potentiometer, meaning it can be set anywhere from 0 ohms to 10,000 ohms. The way we're going to wire our potentiometer allows us to use it to send a varying voltage value to our Raspberry Pi Pico, which some special pins can read, convert and provide a value we can use in our projects. We're going to explain those pins in a few moments, but for now let's get the circuit built. Make sure your Pico's USB cable is unplugged before changing the circuit. Grab your potentiometer, slide the flat washer over the dial. So I've grabbed that here. So grab your potentiometer, slide the flat washer on, and then use the screw to screw the nut on. Then, with the potentiometer legs facing downwards, turn the dial all the way to the left and fit the knob with the coloured line pointing bottom left. All the way to the left. Okay, looks good. Okay, excellent. Leave the LEDs and ground wire in the blue lane in place from yesterday's box, but remove the buttons and all of the parts. This is our starting point. Okay. Now grab the mini breadboard and fit the potentiometer to the front edge facing you. Our diagram uses a generic potentiometer image. However, as you have a fancy panel mount version, your pins will have a whole space between them. Excellent. Look at that. Excellent. Next, we need to connect the potentiometer to our circuit. The right pin needs to connect to the 3v3 out pin, physical pin number 36. 39, 38, 37, 36. The middle pin to GPIO 27, which is physical pin 32. So going back from this one, we've got 36, 35, 34, 33, 32. And the left pin to the ground is any blue lane. Left pin to the ground. And should look something like this. Let's start with a simple program that continually prints the analog reading from our potentiometer. We're specifically using GPIO 27 as this is one of the Pico's ADC pins. But what is an ADC? If you look at our Pico pin map, just make this bigger for you. Okay, so if you look at our Pico pin map again, you'll see that there are 3 dark green ADC pins available on the right. ADC 1, ADC 0, ADC 1, ADC 2. An ADC is an analog to digital converter. The ADC pins on our Pico have the special ability of being able to convert analog input into a digital form we can use. We have to import ADC in our code to use this feature. You can also spot ADC VREF and AG and D pins, but we're not going to go into those in this calendar as we don't strictly need those. The code below imports ADC and sets GPIO 27 as an ADC pin. Then we start a while loop, which prints the potentiometer's value every second. The read_u16 part does this, taking the varying voltage applied to the pin from the potentiometer and scaling this to the range of usable output values between 0 and 65535. For those who want to get technical, the Pico's ADC pins are 12-bit, however MicroPython scales this to a 16-bit range. Run the code below and then try turning the dial, which the values go up and down as you turn the knob from right to left. Run the code below and then try turning the dial. Watch the values go up and down as you turn the knob from right to left. This is where everything above should start to make sense. So let's copy that code. Paste it into here. And then let's plug in the Pi. Okay, let's run it. And there we go. There's the value going all the way up to 65535, and then back down again to the bottom. Activity number 2. Control LED flashes with analog values. So what can we do with this large range of input readings? One thing we can do is use it in our code to control other components such as our LEDs. Whereas previously we have turned the LEDs on or off with buttons, the wide range of output readings allows us to tell our code to do different things depending on whereabouts it is in the range. The code below uses the readings to control how fast your LEDs flash. We do this by making a time delay variable. Variables for time delay. We used a variable to make a counter in day 2, which we constantly updated. This time we're using a variable to allow us to set a value in one place rather than having to search through our code for all the various time delays. For example, let's say we had 5 LEDs in our code and we use a time delay of 1 second. After every flash. From what we have learned so far, we would use time.sleep1 after every flash. That works fine, but it's a bit of a pain to update all of those lines every time we want to adjust the flash speed. Instead, we can create a variable and assign it a name such as myDelay and give it a value, say 1. Then we can change our time delay lines to refer to this variable instead of entering a number directly. Using time.sleep myDelay instead, we can then change our time delay lines to refer to the variable instead of entering number directly. We can then change our time delay lines to refer to this variable instead of entering a number directly using time.sleep myDelay instead. Now, to update the speed of each flash across our entire program, we only have to update the myDelay variable. Whilst we only use the delay once in our example below, we thought it was still a nice opportunity to show you another way of using variables to save you time and improve your code. The example code below takes a reading from the potentiometer, divides the reading to give us a number that's more usable as a time delay, assigns the divided reading to a variable myDelay, uses that delay variable to control how long the LEDs are left on and off to create a flashing sequence. Turn your knob to around halfway to start with. Run the code below, then try adding in the other LEDs and making them flash as well. Or try adding a print line at the end of the while loop to see what value myDelay is using. So let's copy and paste the code. And then let's run the script. So what we're going to do is we're going to turn this dial up. And now we've got LEDs flashing. So the red LED is flashing. And I've just pulled the thing off. So let me unplug the Pi. Plug this in again. Maybe I wasn't in enough. Plug the Pi back in. Okay, what we're going to do now is we're going to run the script. And now what we can see is that this LED is on. And as we turn and change the potentiometer, the LED is now flashing. So I'm going to turn that up all the way. And now there's like a slower rate of flashing. Turn it to about halfway. Then the flashing speeds up. I'm going to turn it back a quarter. And then it's continuing to flash even faster. I'm going to take it another quarter, and then it's really flashing, and then if I turn it all the way to the left, it's probably flashing so fast that we can't even see it, but the light remains on. Fantastic. Activity number 3. Light LEDs depending on the potentiometer value. We can also use the wide range of analog values to trigger an action depending on whereabouts in the overall range we are. We can do this by using if statements again, and this time with conditions that look to see if the value is higher, lower, or between a set range. In our example below, we use a few if statements to check if the reading is less than 20,000, between 20,000 and 40,000, or greater than 40,000. To make our if statement look less than or equal to, we use the operator sign like this. To make our statement look for the value between two numbers, we use a slightly less obvious combination of two operators like this. And to make our if statement look for greater than or equal to, then we use the operator like this. Give it a spin by copying the code below over to Thonny, running it on your Pico, and moving the dial left to right slowly. Remember, the code commentary is there to help you understand each line. Let's copy, paste, and run. Okay, so here we've got an output here happening. Okay, we've got the amber LED on at the moment. Let's turn this all the way back. So when it's off, the red light is showing. So that means if the reading is below 20,000, then the red LED will be on. If we wind that up now, we're on about 12,000, 16, over 20,000, then the amber LED comes on. And when that reaches 40, then the green LED comes on. And that stays on. And then if we wind it back, under 40, and then under 20. So that is working as it should. Activity 4, LED fader using PWM. Now for something a little more advanced but really cool. We're going to fade an LED in and out using our potentiometer. To do this, we need to use PWM. What is PWM? PWM stands for pulse width modulation. It's a type of digital signal where we, over a set period of time, decide how long the signal is on and how long it's off. This very fast on-off signal can create a fading effect for LEDs and can also be used to control robotics components such as servos. Our code needs some values from us to enable it to run PWM for us. Duty cycle and frequency. So what is PWM duty cycle? We can decide how long we keep our LEDs on by changing the duty cycle. The duty cycle is the percentage of the time that our LED will be on. The higher the duty cycle, the longer the LED will be on and the brighter our LED will appear. Duty cycle for the Pico in MicroPython can range from 0 to 65,535, which is handy as this matches the output of our potentiometer. So we can use this value directly without having to manipulate it. What is PWM frequency? Our PWM code also needs a frequency value, which is the number of times per second that we will repeat the on-off cycle. We use 1000 in the example below. So now that we know what PWM duty cycle and PWM frequency is, let's try it out. The code example below introduces a few new elements. Firstly, we need to import PWM. We set our LED pin up a little differently to set it as a PWM output using LED equals PWM pin 18. We set the PWM frequency with PWM.frequency in brackets 1000. We create a variable to store the potentiometer reading and start it at a 0 using reading equals 0. The while true loop then reads the potentiometer value and stores this as our reading variable and prints this for us to view in Thonny. The LED is given this reading as the duty cycle using LED.duty_U16 reading. This is followed by a very short delay, then the loop continues. Copy the code below over to Thonny, run it, and then turn the dial left to right. So it's all the way to the left now, and we're going to turn it all the way to the right. We can see that. So I'm going to turn it all the way down. It's only just on. And then if I turn it all the way up, then that's how bright it goes. So well done, makers. We know today was a little heavier as we introduced slightly more advanced topics such as analog and PWM. So take the time to go back over today's examples and play with the code if you like more practice. Make it, break it, fix it, learn. Today, we have learnt about analog and the difference between analog and digital signals, built a circuit with a potentiometer, learned how to use ADC built into the Raspberry Pi Pico, controlled LEDs with an analog signal, learned about PWM, including duty cycle and frequency. Keep your circuit safe somewhere until tomorrow. Don't take anything apart just yet, and we'll see you then.